Final application we want to discuss is nuclear energy. All right, so nuclear radiation has a ton of energy associated with it, right? You can use it to do a lot of damage. You can do a lot of good with it. And one of the things that we use it for is to have usable energy. And so this is South Texas Project Electric Generating Plant in Bay City. So the City of Houston, City of San Antonio, and City of Austin all get some of their energy from this nuclear power plant. And so when you're using a power plant, when you're trying to get useful energy out, in general, you want a reaction you can turn on and off. So driven reactions are always preferred. So generally, nuclear decay has a lot of energy associated with it, kind of the processes we've talked about. But those are less desirable because you can't just choose to start them, and more importantly, you can't turn them off if you need to. So nuclear fission is a process where a heavy nucleus falls apart into two or more smaller nuclei. And these alpha emission would kind of be the same idea where you lose a helium nucleus. But in general, when we're talking about fission, there are much larger product nuclei that are involved. In nuclear power plants, functional nuclear power plants, fission is the main process that we use. So uranium-235 is a potential candidate. You shoot a neutron at it. The neutron bombards the uranium-235 nucleus, and fission is instigated. So you can see that we start with one large nucleus, and then we get two products out, so two daughters, barium-141 and krypton-92 in this case. All the ideas we've talked about in terms of balancing all the mass and all the charge still applies, right? The same number of protons and number of neutrons start and end. It's just a matter of what atoms, what nuclei are present, and maybe other free neutrons floating around. The energy that comes from doing this process with 1 gram of uranium-235 is 7.26 times 10 to the 10th joules. So for context, burning natural gas is 5 times 10 to the 5th joules per gram. So this is 100,000 times more energy on a per gram basis for whatever uranium you put in. So quite a lot of energy comes out of this process. In terms of what this kind of looks like on an atomic scale, this neutron, when we say it bombards, that word does kind of imply shooting it at it, and that really is the case. This neutron comes in quite hot and hits the uranium, and then that causes it to change temporarily into uranium-236, which undergoes spontaneous fission. It just falls apart. And so it falls apart into the krypton-92 and the barium-141, and a lot of energy come out of that, along with 1, 2, 3 neutrons. And so it's important that those neutrons are created in this fission process, because those neutrons come out of that fission process coming out really hot. What that means is they move fast and they can hit other uranium nuclei, meaning that those other uranium nuclei can then undergo fission. Each of them can then produce 3 more neutrons, which can interact with more uranium nuclei. This creates what's called a chain reaction, right? One fission process causes more fission processes. And not only that, it causes an increasing number. So this is exponential growth, where you start with, say, 1 nucleus, and then pretty soon you can have hundreds, if not thousands, of nuclei involved in the process. Chain reactions result in what are called nuclear explosions. So whenever we use, say, a nuclear weapon, you're relying on an out-of-control chain reaction. You're relying on those processes. In a nuclear reaction, like a power plant, in a fission process, you're having some chain reaction. You still do have neutrons producing other processes, but you're a bit more controlled. You're not necessarily letting every single neutron go on to produce product. And so the fuel for a nuclear reactor is a bunch of uranium metal. These rods here are nuclear fuel. It's just uranium metal, right? Because you need to have a certain amount of uranium atoms close to other uraniums, atoms close to other uranium atoms, just one after the other or all together. So that way the neutrons that come out can just interact with more uranium atoms. So when you run a nuclear power plant, this is kind of an overall way too detailed schematic. But one of the important things is that in your reactor, really the main idea is you just run fission. and that fission produces a lot of heat, and you just use it to heat up water, just like we do in, say, a coal power plant or natural gas. You just heat water, and then that water in a nuclear power plant heats other water because to contain the radiation. So then water that is not exposed to uranium then goes through a turbine, runs the generator, and then that goes out into the great wide open. One of the things you'll note is that this process doesn't directly produce any like exhaust or smog or any sort of like air pollutants that would be coming out. You have cooling towers are one of the common features of nuclear power plants. The Bay City one doesn't use cooling towers, but they're pretty common. What's coming out of there is just steam. And one of the biggest issues when it comes to a pollutant from nuclear power is hot water. The water that's coming out of these things is extremely hot. And so that's why you use these giant cooling towers where all this steam comes out, turning liquid to gases endothermic. So that's just removing heat from the system. There are also, and this is the Bay City plant, use reservoirs of water. They just put hot water into a reservoir. Since the reservoir is really big, it takes that heat, cools it off. So the water can just get really warm. That can lead to issues with algae. That can affect local wildlife populations and things like that. So that's one of the biggest issues. One of the biggest direct pollutant that comes out of a nuclear power plant is going to be heat. In terms of radiation, it's fairly controlled, and you're not producing, say, carbon dioxide or smog, SO2. Any of those air pollutants are really coming out, which is good. So when it comes to using this, we said we needed to use uranium-235. So one of the issues with fission is that it needs to be uranium-235. The natural abundance is 0.72%. So, when you're running this process, if you want a chain reaction, you need a uranium nucleus. It spits out uranium-235. It spits out some more neutrons. You would ideally hope that they hit other uranium-235s. But the natural abundance is 0.72, so if you have one uranium nucleus, for every 100, or one uranium-235, for every 100, you have 100 other uranium nuclei that are not fission active. So all those neutrons just go out, and they don't hit anything that's useful. So you have to create what's called enriched uranium to do fission. So this is one of the first issues. So you need to take your natural uranium and enrich it with more of the uranium-235 isotope. Isotope separation can't rely on chemical means. Uranium-235 and uranium-238 do the exact same chemical reactions, so you use physical means. You use gas effusion. Gas effusion is letting two different gases of different masses pass through a membrane, and the lighter gas will move faster, pass through the membrane a little bit faster. So this mass difference is really small. So in order to get enriched uranium, you need to do this process a ton of times. So in like the 40s, when we were trying to build a nuclear weapon, Oak Ridge, Tennessee was built as a facility to just enrich uranium. So the whole building, and you'll note like there's like cars where, but this is just like a massive building, like football fields worth of buildings. Here are like, storage buildings back there, just huge facilities to do this uranium enrichment, and so eventually a town built up around Oak Ridge to support that, and so this is a really difficult thing to get in, is the uranium-235. It's difficult to get that enriched uranium, and it's once you have it, you got to use it just for nuclear. The only thing you can use it for is nuclear power or bombs. So one of the other things to think about is the products of nuclear fission. So we know we don't make pollution in the sense of air pollution or anything like that. We do have barium-141 and krypton-92 that are the fission daughter products, right? We have daughter isotopes. Are these things stable? Right? What are they going to do? Barium-141 is our first one. And so why is it unstable? Well, it's not too big. But the atomic weight of barium is 137.3. We are quite a bit above that, almost full 4 units. 141 is quite a bit higher. This is unstable, and it's going to undergo beta decay. It has too many neutrons. Similarly, krypton-92, it's not too big. It's small, 36 is well under our threshold. The atomic weight of krypton is 83.8. 92 is a little bit above that. And so there are too many neutrons in this. So this is going to undergo beta decay. And so the fission process happens, your uranium atom is gone, And you now have these barium and kryptons. And the thing is, not only do they undergo beta decay, but their products of that beta decay are still unstable. Barium needs to undergo three beta decays. Krypton has to undergo 4 beta decays until they reach stable nuclei. Zirconium-92 and praseodymium-144. So that's a lot, right? That's a lot of time. And so the biggest issue with fission is nuclear waste. Nuclear fission plants themselves are relatively safe. As far as a power plant goes, you have a big industrial space, you can have some issues. But the fuel is contained. You're not getting radiation off from that. You can use dosimeters to protect your people. Heat is the biggest issue, but you don't produce any air pollution, which is a huge leg up over fossil fuels. But the nuclear waste that you produce, that you have fission products and still unreacted fuel, uranium can still undergo alpha emission. And so if you have some of that left over, what are you going to do with it, right? And so our current strategy is basically put it into the ground. So this is Yucca Mountain. It's the site in Nevada where we just store nuclear waste. We don't have any better ideas. There's not really much you can do with it. You just have to let these things decay in order for them to become stable. That can take hundreds or thousands of years of them just sitting, this nuclear waste just sitting in these barrels in the ground. There is some issue potentially with the waste the barrels break, and generally we're better about those things nowadays than say 40 years ago. And so, but there still are just issues where we need to be aware of this stuff has to sit there in order to become safe. It's just not going to work right now as it stands. So this is the biggest issue when it comes to doing fission. There's no pollution on the air side or the water side except for heat. That's another big issue. But the plants themselves are relatively safe. It's the waste products that they produce. Okay, so nuclear fusion is then an alternate driven process where you take 2 light nuclei and you slam them together to make a single nucleus. And so fusion is another driven process, right? It's not just sort of passive decay with one nucleus just falling apart. Instead, you can make it happen. And so fusion, one of the most common, the form of fusion that drives the sun is proton-proton or hydrogen fusion. You take 2 hydrogen atoms, bring them together, now you get a helium atom. And so this process has a huge amount of energy. You're getting like 4 times 10 to the 11th joules per gram of helium. That is not a lot of helium that you make. You don't need a ton of hydrogen. It's like 10 times more potent than the energy out of fusion or fission. It's really be hugely beneficial. There's no waste, right? It's still nuclear, so you're not producing any sort of air pollutants. There's a lot of heat still that you'd have to potentially deal with, but there's no air pollutants. There's no waste, right? You don't need to worry about that the products are unstable. You make helium-4, which is one of the most stable nuclei. And so you have all this wonderful, all of these really great promising ideas that fusion would be a way to address needs because it's a driven process. We can turn it on, we can turn it off. We get a ton of energy out. Hydrogen is just in the air. You don't need to do enrichment like you do with uranium, which is very expensive. So, you have potentially a really accessible, really promising energy process. Issue is that getting fusion started is really difficult. So if you remember in fusion, you're taking 2 protons and getting them to join into a single nucleus. And when the protons are close together, you have that attractive nuclear force. That was that strong force that we talked about, that when nucleons are touching, they are attracted to each other. But in order to get them from being separate atoms to being together, they need to go through all of that positive repulsion. And that is extremely strong. 2 positive things do not want to come together and eventually touch, right? So over any sort of distance except touching each other, those protons repel each other. So really, this is a kinetic issue. The kinetic barrier to making a fusion process happen is huge. And the solution to get over a kinetic barrier is turn up the temperature. Well, you need millions of Kelvin as the temperature. So that's pretty hard to get on Earth. On the sun, it happens, right? In the sun, it happens that you can drive this. But on Earth, when we want to run a fusion reaction, right? If you're trying to run a fusion reaction, you end up having to put so much energy in that it's not a power plant, it's a power suck, right? You got to put energy to, like, say, burn natural gas, but you get more out of it, right? You light a flame and then it keeps going. Or in the fission process, because they're chain reactions that keep going. In the case of fusion, by the time we get them going, we've already put in so much energy, it's not worth it. in the context of like when we use nuclear fusion in say like a weapon context, you use fission processes to get it started, right? So you need all that energy. The rough amount of energy you need is the energy from like say a fission power plant to get a fusion power plant or to get a small scale fusion reaction even going. So that's just really difficult to get and something that we still need to overcome. Fusion does have other uses. And one of the big uses of fusion is in forming new elements. So all transuranium elements, so that'd be anything with an atomic number greater than 92. So uranium is 92, trans is across uranium. So anything greater than 92, those nuclei are not stable, period. The only way to get them is through synthesizing them. And we do that via just taking two nuclei. So for example, you could take curium, I think, and helium, slam them together, and that's how you make berkelium. Okay, so that's how we make these larger nuclei. You can imagine you take something like, say, uranium, shoot a carbon atom at it, and all of a sudden you get californium and, say, some neutrons pop out of it. It's all still balanced. You know what comes out. But these nuclei that you get, these ones that are way past uranium, lawrencium, 103 atomic number, that is huge. Has a half-life of 0.65 seconds. So these things aren't stable for a long term. This is just how we make new elements. So, you know, on the bottom of the periodic table, you have those elements that are, you know, new elements that are made. You don't discover new elements, you synthesize them. We know what would happen. You need more new protons in the nucleus. It's just a matter of figuring out what combination of particles, what combination of other smaller nuclei do you need to shoot together to get what you're after. And as they get bigger and bigger, they get more and more unstable, and it becomes harder and harder to find the right combination of other nuclei. So when you want to do this, if you want to do these nuclear collisions, you use what's called a particle accelerator. So this is a photo of the synchrotron particle accelerator at Fermilab. That's in Batavia, Illinois, not too far from Chicago. So to give a reference, these green things are forests. So those are trees. This is like an office building back here. That's a lake or pond. But so this is a very large facility. These are very, very large facilities where you're moving these atoms. And, you know, you're trying to slam together two positively charged particles. Not protons is +1+1. Here you're dealing with, you know, plus 50s, plus 90s. These are really highly charged particles. They don't want to hit each other. So you use these giant structures called particle accelerators. And what actually does the accelerating is this object right here. This is like roughly the size of like a bus. These are really large magnets that you're using to move the electron or the nuclei at really high speeds in a basically a circle. They keep going faster and faster, and then they can collide with each other. And so this takes a huge amount of energy, right? You can see this isn't really something we could necessarily do to get useful energy out so far. It's also worth noting that these ideas of using fusion to create anything, any sort of new nucleus is true in general. All nuclei that exist were created via fusion, right? Everything started with, say, protons, and then they come together. And in, say, you know, the sun, we're not making much beyond, say, carbon. Okay, so, but they come together to, say, protons. Come together to get a helium. Two heliums come together, you can get beryllium, and kind of move on like that. These temperatures, in order to get anything beyond, say, carbon, so 6 protons, you need temperatures that are hotter than the sun. Okay, so bigger stars, things that are bigger. Because they're bigger, they're heavier, so their middles have, the middle of that star would have more pressure on it. It's easier to get those atoms closer together. And so, you know, you can get up, say, iron that way. So like really, really, really big stars are, say, synthesizing up to iron using just those fusion processes. And if you want to get higher than that, you need even higher amounts of energy, which require, like, say, 2 stars to hit each other, or stars to explode, or things like that. We have really, really high energy cataclysmic events. And so one of the ramifications of that is the atoms that make up our solar system, for the most part, came from another star. The sun can produce, it doesn't do, but the sun can produce up to carbon. It's carbon or oxygen in there. Anything beyond that had to come from, say, another star, because our sun's not big enough. And everything past iron, which there's plenty of gold, silver, uranium on this planet, mercury, lead, those things had to come from other stars and other places. And those stars exploded and ended up here. They ended up in you. Participation 1125, question 4.
Complete each of the following statements. A, nuclear blank is the primary process used in nuclear power plants. B, nuclear fusion would be preferable for energy due to the minimal blank created. And C, nuclear fusion is not used in power plants due to the extremely high blank required. This is the fourth question on participation 1125, due Tuesday, November 25th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, complete each of the following statements. A, nuclear blank is the primary process used in nuclear power plants. B, nuclear fusion would be preferable for energy due to the minimal blank created. And C, nuclear fusion is not used in power plants due to the extremely high blank required.
All right. Nuclear chemistry, going back, first kind of set of videos is all about like individual nuclei, why they decay, if they decay, predicting what they're going to do. And then applications this time, half-life and dating, and then kind of not necessarily the application of radiation effects on humans, but yeah, how that applies to nuclear medicine and then nuclear energy.
All right, 4 questions on participation 1125. If you want to find all 4 of those questions, get them answered, get those answers submitted over on Blackboard by Tuesday night. Midweek 14 homework is going to be due Wednesday over on Active. Before just a little bit more chemistry before you leave, before we end for Thanksgiving. Otherwise, this is it for this week. There's no other sets of videos. The participation will go live Tuesday night. That'll be in chapter 21. Next week, we'll have 2 sets of videos. And then again, on Wednesday, we'll do the participation follow-up. The lab practical will be after that. That's on Wednesday on campus. And we'll do the lab technique presentation will be due next week as well. If you have any questions about completing anything, let me know. Otherwise, make sure you take care of the participation in the midweek. You're not done yet. Otherwise, enjoy your break. I'll see you next week. Bye-bye.